So Swiss Re's motto is obviously to make the world more resilient, and we do have a big life and health business unit. As such, we have a lot of projects around AI and resiliency involving electronic health records. Instead of picking one today, I thought of instead of zooming out a little bit and try to generalize some learnings, but also most of all some challenges that we have around mining electronic health records. So I hope you will find them interesting, and that I can also get some tips how to solve these challenges throughout the presentation. Let me start by zooming a little bit back. What do I mean by electronic health records, or the EHR data, and why is it so important for a life and health reinsurer, or even for life insurer like Swiss Re? Broadly speaking, EHR data, so it's a electronic health record, so it's a digital collection of medical data. Typically, it includes demographics data, like the age, the gender. It also includes medical diagnosis, of course. Sometimes very granular, the ICD level, sometimes a bit less granular. It may include sometimes things like blood pressure, but also weight, BMI. Sometimes we have very granular drug information. And whenever someone goes to the hospital, usually we also access very granular hospital admission information. So one hospital admission may be dozens of records of information on the diagnostics, the procedures, and so on and so forth. Of course, the CHR data is leveraged in many places, first and foremost for within health systems, say at the hospital precisely. In our case, we're not interested by the EHR data of one individual or of a few individuals. Instead, we work, and it will be a bit the focus of this presentation, with very large actually, EHR data sets, sometimes commercially available, sometimes only for research purposes, that are, and it's also important, fully anonymized, without any way to de-anonymize it. I give some examples on the top left. So we have the figures from the so-called Truven Market Scan dataset, which is a dataset covering 40 million US inhabitants, age 0 to 65. So that's about 5 billion external consultations, 2 billion drug payments, and so on and so forth. So it gives a little bit the scales. It's a lot of data. It's not always that big. We also have data sets, for instance, the Fin data set in the UK covering 10 million people. So Exploris data set in the US covering about 4 million people, and so on and so forth. Now, why is this data set so important for us? To answer this question, I need to make a little step back on what do we typically have. What does a life insurer or life reinsurer typically has in terms of data for life insurance? So you typically have two data sets. The first one is the exposure, so who is insured, age, gender, medical conditions at time of underwriting, so when you buy a life insurance. Also things like smoking status, obviously, extremely important. So all this data is basically the data you supply when you buy a life insurance. So that's what we call the exposure. It's a data set which, of course, is static. And so you don't send information anew to your life insurer or even to a life reinsurer. And then you have the claims data set, which is basically a data set which is much smaller, which contains all the payouts. So to make it simpler, the mortality events, critical illness. And of course, needless to say, this data set is much smaller, of course, thankfully, but also extremely lagged with regards to the exposure data set. So these events may happen 15 years later. So I think you start to see a little bit the issue that with these two data sets, it's only really a tiny portion of the data at hand when it comes to someone's health. And because you cannot track someone's health, you don't have any feedback loop on someone's health, how is someone evolving, medical conditions, it's really not enough to understand the evolution of the risk. And that's where the EHR data kicks in. So I take a bit the image of the iceberg. So as such, life insurance has really the tip of the iceberg, and most of the data is underneath. So with EHR data set, you really can bridge the gap, assuming, of course, you are able to map correctly, say your insurance features with the data from the EHR data set. And what to do from that? Well, you can do many things. You can create new products. You can understand the risk for niche markets. For instance, let's say, I don't know, dementia, for instance, there is no product for that. You can create a new product around dementia, measure it, understand what are the drivers, what are the complications, you can refine, and sometimes you can even insure pockets of risk that were not insurable before. Other applications, it's about also refining some underwriting assumption, like what is precisely the impact of BMI or of smoking, and so on and so forth. I would like now to present you with one standard application, which I will call the diabetes offering. So it's a very standard model. Well, so you will see about it. So what do I mean by diabetes offering? Let's assume you are a life insurer, and you have, for instance, 1 million people insured. So 1 million people who bought a life policy. Now, a key driver of the risk is diabetes. It leads to severe comorbidities. It leads to cardiovascular problems, to skin problems. So one idea is to mitigate this risk simply by selecting the people in your portfolio the most prone to become a diabetic and engage them into mitigation action. Early trigger, we beat with coach, with dedicated programs, and so on and so forth. Now, of course, to do this, you need to precisely identify these people, and you understand that with the traditional exposure and claims data, you simply do not have this capability. So this is where Inforce client data contains the predictive features, but not the historical data to do the training. And this is where the EHR dataset kicks in. So the idea is to train a diabetes model with the EHR dataset, replicating very carefully the information within what we call the Inforce client data to identify who is the most likely to become diabetic. How does it work under the hood? So as I mentioned, one thing is to be extremely careful to define a common ontology between your EHR dataset and the Inforce client data. So data scientists cannot do it on their own, as they have to work carefully with product owners, with data experts, with insurance experts, and so on and so forth. Usually, you end up with a typical feature space containing information like age, gender, BMI, and so on and so forth. And of course, you have the target from the EHR dataset you have where you can track individuals year on year. You can see who will have become diabetic or not within the next 5 years, and you can binarize your target like that. It's a standard binary regression model, so you can use, for instance, logistic regression. Please note that although it's a binary, it doesn't mean necessarily the outcome of the model is a class. Quite the opposite. When we talk about risk, usually classification tools like confusion matrix and so on are not very meaningful. What is meaningful to understand the risk is more to keep the continuous indicator like a probability. Here in this case, it makes a huge difference for the economics of the product to know that the most likely individual has to have diabetes. The probability is it 20%, for instance, or is it 5%? So we need to have this scale in mind, which we would lose with a pure class approach, because simply the economics of the approach is not the same if it's 20% or 5%. In one case, it may be viable and worth it to trigger this plan. In the other case, not. So that's a standard problem, standard machine learning problem. We see, so there are some details, of course, and a lot of complications to create the product itself, but we see how it helps basically to make the world a bit more resilient. Now, in the next slides, I'm going to challenge a little bit this standard problem. I'm going to stretch it in different dimensions to show a bit of complexity and the actual challenges that we do face at Swiss Re, mining electronic health records. The first challenge, obviously, is around stationarity of the data. And dynamicity. When we do this approach, there is an underlying assumption that the data, this EHR data, for this longitudinal data approach is stationary. Of course, it doesn't hold. It's really too good to be true. And I think the COVID is a great example of that. So COVID has created strong trends within the diagnosis. Of course, some of them directly COVID related, but some others only indirectly related. I'm thinking, for instance, mental health issues or musculoskeletal disorders just from working from home for too long and having maybe less social life. All this, you will be able to observe a trend in your data set. with a longitudinal data approach, you will not be able to capture it properly, basically. And first and foremost, you do not have, at the individual level, you do not have a factor telling this individual has been working from home, for instance. So you cannot find a good individual-based feature capturing at the individual level this increase in trends. Vice versa, so it's a perfect approach to capture these trends is obviously a macro-based model, so at the population level, where we work on time series. So once you work on time series, everything is easier because you can make your time series stationary, you can capture dynamicity, and for instance, you can feed using expert data, you can feed an external factor, something like average hours worked from home for this given population, or this given cohort, for instance, male 30 to 40, maybe with this data somewhere, and then you may be able to capture it. Now the issue is, of course, how to mix the best of both worlds. And we tried quite a lot to feed these macro indicators into the individual-based model, but of course, it really doesn't work. So at the individual base, usually you use techniques quite aggressive, like, I don't know, gradient boosting, for instance, to really go deep into the conditionality of the features, the intrications of the feature space. At the macro-based level, you use models way more defensive, linear, and hence it's very hard to mix both worlds. It's all the more harder that EHR data sets usually have a strong sourcing bias. That is, usually healthy people do not get their blood pressure measured every month, so there is a natural tendency. Simply to have populations tracked which are a bit higher prevalence of disease. In this plot on the right, so it's we used to mine the Exploris data set, also covering from the US, so you can see the lung cancer incidence rate in orange. So at the beginning of the data set, it was not stationary. The population was too small, so the prevalence of lung cancer was lower than the CDC in blue. And once it became a bit of a critical site, of which is now about 5 million people, we can see that the lung cancer prevalence is way too high. This data set is, by the way, amazing when it comes to making BMI models and so on. But for instance, for this one, it's not really good. So one answer to that is obviously to use shorter windows, because it's really, at least that's the way we do it. So when you have EHR data sets of 40 million people, for instance, you do have the luxury not to take the last 5 years to train your data, but for instance, to take only the last 2, so to restrict as much as possible. That way, you intrinsically capture only the latest dynamicity you have in the data. Let's go to another challenge, which also connects to this one, how to go long-term. Indeed, here in this standard diabetes model, you recall my target is, will someone have diabetes over the next 5 years? So 5 years is indeed a time range you may hope to get from EHR datasets. But what about a real insurance product, which is more 20 years ahead, for instance? So you don't buy a life insurance policy only for the next 5 years. That's way too short. So it's quite clear that EHR records do not have 20 years of data. So supervised learning approach will not work. And all the more, anyway, providing they have had 20 years of data, because of the stationarity issue and dynamicity, you definitely don't want to use such a long data for your model. So how to cope with this? That's definitely a challenge we face for this type of products. One idea is really turn the table around and instead of modeling from now on until 20 years, to do step by step, namely year by year, for instance, or it can be 2 years by 2 years, and to model all the single transitions step after step until from next year until 20 years ahead. What I mean here is that any single feature you use in your model needs to be simulated. So you need to have a BMI model, a function, of course, of available information. So current BMI, age, gender, anything you need, but also maybe footsteps, right? How many footsteps per day? Maybe you do have this data. Then the BMI simulations as an outcome, not expected value, but simulations will be fed into maybe a diabetes model. So again, we roll the dice. Will you be diabetic next year or not? And so on and so forth. Of course, this model has quite some complexity. To make it robust takes a lot of time, but it does have the beauty that you can link, so elegance, I would say, that you can link somehow footsteps per day, for instance, to mortality. So the link is not going to be strong. It's done throughout all these intermediary steps. So that's one way to do it. There is another issue going very long-term time-wise, is obviously, so now we link back to the topic of dynamicity, how to link basically long-term trends. So a machine learning a supervised approach to train a transition model like BMI will capture very short-term trends, and it will extrapolate it. So if there is drift in your historical data the last 2-3 years, the supervised learning approach will extrapolate it. But this drift may not be the one, of course, for the next 20 years. For instance, if you have, say, a new bill in the country, a new law saying that cigarettes are absolutely forbidden to be sold to less than 25 years old, who knows? Obviously, we understand, experts understand that there may be consequences for the smoking prevalency, but the model doesn't know anything about that. So you need to avoid the strong asymmetry of the model, which may really bias the results. You need to find ways to feed it in. There are different techniques for that. For instance, if you have a linear model, you can use very basic. You can use the positivity constraints to enforce a direction. With this scenario-based approach, the beauty is that you can really look, for instance, at all the scenarios coming out of the smoking model, and this year after year, and you can adjust them simply. You adjust them to match the views that you have, and then you feed them back into the model. And subsequently, the diabetes model, which takes the smoking scenarios as an input, will take into account your scenarios. Same thing with the cancer model, same thing with ultimately the mortality model. So that's one way to do it. Third challenge, and also the last that we have, that you may face with the while mining electronic health records, at least we face at Swiss Re, is to go in the tail. What I mean here is a tail risk. So we talked about mortality event. Obviously, it's a very imbalanced and thankfully imbalanced event. Let me take another example. And for this, I need to dive a bit more into the insurance technicality. So let's look now at medical claims. So what I mean here, so that's because I work with the Trovan data sets, let's talk about dollars. Let's assume we have a typical reinsurance product called an excess of loss cover, namely that we cover any claims per individual per year in excess of a given deductible. This deductible may be of, for instance, $50,000, just like it may be much higher of $500,000, even $1 million. You have markets for that. There is need for some primary insurer. There are the needs to get protection in front of this type of claims. Why is that? Simply because, especially in the US, you do have a strong medical inflation of 7% per year, maybe, leading, and you do have these catastrophic claims of $1 million plus per individual, and it's not rare to have a 10 million, well, it is rare, but it can happen to have $10 million per individual per year. So same, you can solve it with the machine learning problem. In fact, you should try. You should really, again, be extremely careful around the data assumptions that you make. So here, someone has never bought an insurance for next year exactly on the 31st of December, so you always have a blank window. So here we assume together, we work jointly with underwriters, we assume there is 4 months of blank windows, and you have the target variable next year, which is the excess loss. So loss in excess of 50,000. In this supervised modeling approach, it means it's a target made mostly of 0, 0, 0, and all of a sudden a claim which may be very large. So claim distribution, I show it here, and at the bottom, usually it's so claims from usually are around, I don't know, $2,000, $3,000. These are the claims that we may face every year, and you have this tail risk, which can go quite far. So with a deductible of $50,000, we have a risk to exceed this threshold, which may be around 3%. Once you go at 500,000, it may be 1 in 10,000. And at $1 million, it may be, I don't know, one in I forgot the number, but 1 in 50,000 maybe, so extremely small. Supervised learning approach will not work in this case. So what are the techniques we have? So first, supervised learning may still work actually. You just need to be a bit careful. So techniques like, I don't know, random forest should really be avoided simply because they may conclude on a zero risk. So they may zoom out thanks to the trees. They may isolate quite some large chunks of data where they conclude there is no risk. And that, of course, is definitely the wrong answer. To prevent that, linear models, so I don't know, for instance, well, for the probability itself to exceed something like a GAM model may be extremely useful. But I think the most promising is also to join forces with actuarial approaches, which of course have a distributional point of view in mind. So their technique would be to fit the distribution on the data, and then to apply, for instance, a Pareto or log normal distribution or a binomial. I mean, they have all types of distributions here. Make sure you have a very good fit in the tail, and it's hard because usually your fit is done on the bulk of the data. Then once you have this distribution, so actuaries then try to use factors, what they call the loadings, to weight the tail up and down with you have, I don't know, diabetes, with you have this, with you have that, in order to still stick to the machine learning approach. One idea is simply to express all the parameters. So you have 3 parameters to describe the distribution, to express them as a function of the feature space, and you end up like here with a severity curve. So here you have the log time claims with a severity curve describing per individual, basically, from which, since you have the full parametric, the full mathematical expression, you can sample at any deductible, and you can have the expected severity. So that's a very promising approach. But in general, this challenge of machine learning in the tail is a very hard one, which we face not only for medical claims, but in many conditions. I will conclude on a few. I don't want you to leave thinking Swiss Re has any challenges but no solutions. So I want to conclude this with a few learnings, also because it was the title of the talk. Something that I very often mention: so risk is not about probabilities or distribution. Sorry, that's the opposite. So risk is about probability or distribution. It's not that much about expected value or classes. So the expected value of a claim is around $3,000. It doesn't tell you anything about the tail. Once you do a classification like cat or dogs, basically you lose the probability and you lose information on the risk simply. So that's really something to keep in mind. Whenever you work with external data, so how was it sampled? And we always have new findings here. We need to be very careful. I think we should keep in mind always this very careful data engineering that you need to do in order to mimic, to correct the right sample of the EHR data set, to map it with the real world. Sometimes we end up with feature space that are really tiny, but that's just a problem we have. It's a business problem, and therefore we use less than 1% of the EHR data set. But that's the reality of the business process underneath. And then the last tip, so really to be aware, and this really generalizes much beyond EHR data sets, to be aware of the knowledge asymmetry between experts and the model. That is, if experts know there will be a shift because of this and that, and the model doesn't know it, or the data doesn't know it, then of course you create complete mistrust in the model. So you need to find ways, either you need to acknowledge it, the model doesn't know that, or you need to find technical levies how to feed it in the model, basically. With this, and I think just in time as well, I would like to close the presentation here. Thank you.